Let's begin our study on nuclear physics with a brief revision of atoms. So as we mentioned previously, an atom consists of a nucleus in the middle, and this nucleus contains protons, which have a positive charge, and neutrons, which are neutral. And orbiting the nucleus are the electrons, which have a negative charge. Now we generally represent an atom of a particular type of element, so in this case being lithium, as having an atomic number denoted by Z, being the number of protons in a nucleus, and a mass number A. So in this case, Z is equal to 3, being the number of protons, and the mass number is 6. So the number of neutrons is the mass number minus the atomic number, which is 3 in this case. And the mass number A is also called the nucleon number. Now isotopes are nuclei that contain different numbers of neutrons, but the same number of protons. So in this case over here, we have the lithium-6 isotope, which has 3 protons and 3 neutrons, so the mass number is 6. And there's also the lithium-7 isotope. So that has the same number of protons, but a different number of neutrons. So lithium-7 has 4 neutrons, and lithium-6 has 3 neutrons as we determined. And lithium-7 is the most abundant isotope of lithium on Earth. So it has 92 to 98% abundance, whereas lithium-6 has 1.9 to 7.8% abundance. So these are the most stable isotopes of lithium found on Earth. Now a nuclide is a nucleus with specific numbers of protons and neutrons. So in this case, lithium-7 is a nuclide with 3 protons and 4 neutrons, and lithium-6 is another nuclide with 3 protons and 3 neutrons. Now the mass of a proton is very small, so it's around 1.67 by 10 to the minus 27 kilos. And similarly, the mass of a neutron is also small, so that's slightly heavier than the mass of a proton, but it has a similar order of magnitude. So instead of kilograms, we use atomic mass units to represent the masses of nucleons. So if we define one atomic mass unit as 1/12 of the mass of a carbon-12 isotope, so 1/12 of the mass of a carbon-12 isotope is around 1.66 by 10 to the minus 27 kilograms. And therefore the mass of a proton in atomic mass units is around 1.007 AMU, which is also written as U, and the mass of a neutron is 1.009 atomic mass units. And these are the units we'll use from now on when referring to the mass of a nucleon or nuclide. The nuclear strong force is dominant at the nuclear scale and dominates the interactions of nucleons, being protons or neutrons. So the strong force is one of 4 fundamental interactions, and it's the strongest in the range of 10 to the negative 15 meters, which is 1 fermometer, and this is the scale of the nucleus. So 1 thermometer is slightly more than the radius of a nucleon, being a proton or neutron. So note that the nuclear strong force also holds a nucleon together. So it's much stronger at the scale of 0.8 thermometers, which is the scale of a nucleon, and the nuclear strong force is weaker at 1 to 3 thermometers, which is the scale of the nucleus. Now it's 100 times stronger compared to the electric force, or the Coulomb force, which recall is the force that holds the atom together. So this is the force responsible for attracting an electron to the nucleus. And a nuclear strong force is 10 to the 6 times larger than the weak force. So the weak force is responsible for some nuclear phenomena, such as radioactive decay, where a larger nucleus, such as radon-222, decays into a smaller nucleus, being polonium-218 in this case. So this nucleus gets broken up into a smaller nucleus and loses an alpha particle, being a helium particle. And we'll look further into radioactive decay later on. And furthermore, the nuclear strong force is much stronger than the gravitational force, which we've seen acts on 2 masses. Now the strong force is actually complicated, so it's not as straightforward as the electric force, for example, or the gravitational force, being inversely proportional to the square of the radial distance between 2 charges, and it needs treatment from particle physics to adequately understand it. So for example, if we look at the nuclear strong force between protons and neutrons in the nucleus, then this force is mediated or made possible by smaller particles being pions, and a pion is a subatomic particle that's made up of smaller particles, being a quark and an antiquark, and pions are exchanged between a proton and a neutron, and these particles decay due to the weak interaction between the quarks. So remember, the strong force between the quarks also holds nucleons together. So for example, we have a proton here, and this force between the quarks is mediated by gluons, which are massless elementary particles. So this is just the basic introduction to how the nuclear strong force works. Now possible nuclear reactions, such as fusion, fission, and also radioactive decay, and we'll look at each of these in more detail, are constrained by the law of conservation of nucleon number. So remember, the nucleon number is also the atomic mass number of the nuclide we're looking at. So essentially, both mass and charge are conserved in a nuclear reaction. Now let's look at a brief example to illustrate this. So we have the radioactive decay of radon-222. So radon has a mass number of 222 and 86 protons. And the nucleus of radon decays into a smaller nucleus, being polonium, which has a mass number of 218 and 84 protons. And in this process, an alpha particle is shed. So we have a helium, which has a mass number of 4 and an atomic number of 2. So in other words, because radon has a very large nucleus, it sheds nucleons quickly. And that's basically what alpha decay is, being one type of radioactive decay. So the sum of the protons and neutrons remains the same after a nuclear reaction or decay, and the number of protons also remains the same. So here we see that the sum of the mass numbers of polonium and helium is equal to the mass number of radon. So that means mass is conserved when radon decays to polonium. And when we look at the conservation of charge, we only focus on the charge of the protons in a nuclear reaction. Whereas in chemistry, when we dealt with chemical reactions, we focused on electrons. And remember that the atomic number, being the number of protons, identifies the type of element we're dealing with. So by the conservation of charge, we see that the number of protons in the polonium nucleus plus the number of protons in the helium nucleus is equal to the number of protons of radon. So both mass and charge are conserved in a nuclear reaction. The behavior of the constituent particles of a nuclear reaction is constrained by the laws of conservation of energy, energy mass equivalence, so noting Einstein's famous formula E equals mc², which we'll explain in a bit, and also the conservation of momentum. So for all nuclear reactions, mass and energy may be exchanged due to mass energy equivalence. So if you consider two stable isotopes of hydrogen, being protium and deuterium, where protium has one proton in a nucleus and no neutrons, and deuterium has a proton and neutron in its nucleus, so under very high temperatures, the nuclei of protium and deuterium can fuse together to form a heavier element, being helium, which in this case has 1 plus 1 equals 2 protons, and a mass number of 1 plus 2 being 3. So this is one of the helium isotopes. So we expect mass to be conserved in this nuclear reaction. But the mass of the helium isotope turns out to be less than the mass of the hydrogen isotopes. And that's because energy is released in the form of gamma radiation when these two nuclei fuse together. And this is why energy is equivalent to mass, because energy is released when this particular element or mass is formed. So for example, consider the mass of a deuteron, which is a nucleus of deuterium, or this hydrogen isotope. So that's measured to be 2.014 atomic mass units using mass spectrometry, and noting that the mass of a proton plus the mass of a neutron in its nucleus is equal to 1.007 atomic mass units plus 1.009 atomic mass units. So the mass of a proton plus the mass of a neutron is actually slightly higher at 2.016 atomic mass units. So the mass defect, denoted delta M, is the difference between the mass of the bound nucleus and its constituent nucleons. So in this case, the mass defect is the mass of one proton plus the mass of one neutron minus the measured mass of a deuteron. So the missing mass was converted to energy when deuteron was formed. And Einstein's equation, E equals mc², quantifies how much energy mass contains. So essentially the mass difference, or mass defect, quantifies the amount of energy needed to break the deuteron into a separate proton and neutron. So the binding energy of the nucleus quantifies how strongly the nucleus is bound, and that's equal to the mass defect by the square of the speed of light. So if we recall, one atomic mass unit is 1/12 of the mass of a carbon isotope, which was 1.6605 by 10 to the minus 27 kilos. Then we can calculate the energy equivalent of one atomic mass unit. So we have E equals mc². So m multiplied by the square of the speed of light, which is 2.998 by 10 to the 8 meters per second squared. So that'll give us a unit of joules, which will convert to electron volts. So 1 electron volt was 1.602 by 10 to the minus 19 joules. So that'll give us 931 by 10 to the 6 electron volts, or 931 mega electron volts. So from this, we can calculate the binding energy of deuteron by multiplying the mass defect, which is delta M, which is equal to the mass of a proton plus the mass of a neutron, being 2.016, minus the measured mass of deuteron, which is 2.014 atomic mass units. So if we used a few more decimal places, we'd get the mass defect as 0.0024 atomic mass units, and then multiply this by the energy of one atomic mass unit, which is 931 mega electron volts per atomic mass unit. So that gives 2.23 mega electron volts. And therefore, if we want the binding energy per nucleon, we have two nucleons in a deuteron, so that was one proton plus one neutron. So that gives 1.12 mega electron volts per nucleon, which is a lot larger than their ionization energy. So the average binding energy per nucleon, considering the different isotopes, are plotted here versus the number of nucleons in a nucleus. So if we look at deuterium, it has an average binding energy close to 1.12 as we calculated. And nickel-62, which is not shown here, has the highest binding energy per nucleon. So typically when two nuclei are smaller than nickel, then they get fused together to form a larger nucleus. And the binding energy per nucleon increases, so energy is released in the process. But if a nucleus is larger than nickel, it gets split into two smaller nuclei, and the binding energy per nucleon also increases, so energy is again released. So basically the first case is nuclear fusion, where two nuclei are fused together, and the other case is nuclear fission, where a larger nucleus is split into smaller nuclei. And we'll look at these in more detail. But essentially energy may be released in nuclear processes in the form of kinetic energy of the products, or as photons, so for example being gamma radiation as we saw. Nuclear fusion is the process that powers the stars. And a typical example is the Sun, where inside the core, hydrogen nuclei get fused together to form the heavier element helium. So in the Sun, the core is extremely hot, at around 15 million degrees Celsius. So in contrast, the temperature at the surface of the Sun is around 5500 degrees Celsius. So essentially, two hydrogen protons collide at extremely high speeds. So essentially the first fusion is the most difficult because the two protons have to collide at a significant speed to overcome the Coulombic repulsion force, so they get close enough where the nuclear strong force takes over. So when two protium nuclei fuse together, a deuterium is formed, which has a neutron, and essentially one of the protons decays into a positron, which has the same properties as an electron, but a positive charge, and also a neutrino. So this type of radioactive decay results in a neutron being formed in the deuterium nucleus. So as we can see, by the conservation of nucleon number and charge, we have two protons on the left and one proton plus a positron on the right. So that's two positive charges. And in terms of the mass number, we have 1 plus 1 equals 2. And the next step in the nuclear reaction is where a deuteron gets fused with a protium nucleus. So in this step, a helium-3 isotope gets formed, which has two protons and one neutron, and gamma radiation gets emitted. So recall the mass defect, where the mass of the product will be less than the mass of the reactants. So gamma radiation was emitted to form the nucleus of helium. And in the next step, two heliums get fused together to form a helium-4 isotope. And two protons are lost in the process. So as we can see, the nucleon number and charge is conserved in the nuclear reaction. So in this step, the energy in this case would be converted into the kinetic energy of the protons, which fly off at some velocity. So note that the fusion process is not perpetual. It'll stop eventually when the temperature of the core cannot sustain a fusion reaction. So in other words, larger stars than the Sun will have a hotter core, so they'll be able to fuse heavier elements than helium. Nuclear fission is where the nucleus of an atom gets split into two or more smaller nuclei, as well as subatomic particles like neutrons. And nuclear fission may occur spontaneously. So if a nucleus is unstable, it'll split by itself without the input of external energy, or it may require energy input, which depends on the binding energy of the nucleus. So if we bombard uranium-235 with a neutron, this large nucleus is going to become more unstable and break up into two smaller nuclei, being barium-144 in this case, which has 56 protons, and krypton-89, which has 36 protons. And the nucleus of uranium is going to lose more neutrons. So what we'd get in this case is 3 additional neutrons. So we get 3 neutrons by the conservation of nucleon number. So 144 plus 89 plus 3 gives 235 plus 1, or 236. And furthermore, by the conservation of charge, 56 plus 36 is 92. So note that this is one way that uranium-235 can undergo nuclear fission, but it can break up into 2 other types of nuclei. Now uranium-235 is fissile, meaning that the products on the right hand side are more stable, such that energy is released when this nuclear reaction takes place. And the other most abundant isotope of uranium, being uranium-238, is not fissile. So it's hard to break it up into smaller nuclei. So uranium-235 has 0.7% abundance, and uranium-238 has 99.3% abundance. So natural uranium will mostly contain the non-fissile isotope. Now this reaction releases a small amount of energy, but in reality you'll have more of these uranium nuclei undergoing fission. So for example, this emitted neutron will collide with another uranium-235, and this neutron will collide with another one, and so on, causing a nuclear chain reaction, which results in a massive amount of energy being released. So given that there's not much of this fissile isotope compared to the non-fissile one in natural uranium, the uranium must be enriched to separate these isotopes. So for example, a gas centrifuge can be used to separate them via the centrifugal force based on their mass. So essentially, you need 85% of the fissile material for a nuclear weapon, and around 3 to 5% for a nuclear reactor to generate nuclear power. So therefore the nuclear reactor won't explode because you'll have less of the fissile material colliding with these neutrons. And therefore the nuclear chain reaction won't be as devastating as for a nuclear weapon. Radioactive decay is the spontaneous transformation of a nucleus to one or more different nuclei. So we see different elements on the right hand side, contrary to chemical reactions. So the decaying nuclide, in this case being radon-222, is the parent, and the resulting nuclide, being polonium-218, is called the daughter. So this is an example of alpha decay, and we'll look at the different types of radioactive decays later on. Now generally the time at which an individual nucleus undergoes radioactive decay is not determinable, but the decay rates can be described using probability. So for example, we have a sample of many nuclei, and we find the average time taken for the number of nuclei of an isotope in a sample to decay. So essentially, the rate of change of the nuclei over time is minus the decay rate by the current number of nuclei at time t. And if you've taken calculus, this is an ordinary differential equation, and we won't solve it here. We'll just write down a solution as the number of nuclei remaining at time t is equal to the initial number of nuclei by e to the minus the decay rate multiplied by time t. Now the half-life, denoted T1/2, of a radioactive material is the time it takes for half of the initial number of radioactive nuclei to have spontaneously decayed. So if we substitute for the number of nuclei at time t as half of the nuclei remaining, that's equal to the initial number of nuclei by e to the negative lambda by the half-life. So if we cancel out n0 and take the natural log of both sides, we get the natural log of 1/2, or 1/2 is 2 to the minus 1, is equal to minus lambda T1/2. And this is the same as minus the natural log of 2, using the rules for logarithms. And then we can cancel out the negative signs. And therefore the half-life is the natural log of 2 on the decay rate. So we can turn this equation around to relate the decay rate to the half-life. So we can use the material's decay constant to predict the number of nuclei remaining in a sample after a period of time using this equation, or the age of a material if the initial amount of material is known. So if we divide through by the initial number of nuclei and take the natural log of both sides, we get the natural log of the remaining number of nuclei on the initial number of nuclei being equal to the negative of the material's decay constant by time. So as we can see over here, the half-life of radon-222 is around 3.8 days. So at every half-life, we have half of the sample decaying. So we're left with 50% of the nuclei after every half-life. So at 2 half-lives, we're left with 25%. And after 3 half-lives, we're left with 12.5%, and so on. And generally, different unstable elements and isotopes may have vastly different half-lives, which can range from the fractions of a second to billions of years. So essentially, some isotopes are way more unstable than others. Find the number of protons and neutrons contained in the following nuclide, and also write symbols for the other stable isotopes, given they contain 31 and 32 neutrons. Well, here we have the mass number, or nuclide number, being 56, and the atomic number is the number of protons, being 26. So therefore the number of neutrons is the nuclide number minus the atomic number, which gives 30 neutrons. Now the isotopes contain the same number of protons, being 26, and the isotope with 31 neutrons thereby contains 26 plus 31 nucleons, being 57. And similarly, the other isotope contains 26 protons plus 32 neutrons, which is 58. So these are the symbols for both isotopes. Find the maximum wavelength of electromagnetic radiation that can be used to photodisintegrate a deuteron. And we're given the following constants. So recall the energy of a photon is Planck's constant by the frequency of light, and that's equal to Planck's constant by the speed of light on the wavelength. And therefore, turning this equation around, we get the wavelength is equal to Planck's constant by the speed of light on the energy of the photon. So the minimum energy required to photodisintegrate the deuteron is the binding energy of the nucleus. And therefore the maximum wavelength is Planck's constant, which is 6.626 by 10 to the minus 34 joule seconds, multiplied by the speed of light, which is 2.998 by 10 to the 8 meters per second, and that's divided by the binding energy, which is 2.23 mega electron volts, or multiplied by 10 to the 6 electron volts. And we want to cancel out the joules, so 1 electron volt is 1.602 by 10 to the minus 19 joules. So as we can see, the joules cancel, the seconds cancel, and the electron volts cancel, and we're left with a wavelength in meters. So if you calculate this out, you get 5.57 by 10 to the minus 13 meters. Find the nuclear binding energy per nucleon of copper 63, and we're given the atomic mass, and we're also given the mass of a proton, neutron and electron as follows in atomic mass units, and the energy equivalent of one atomic mass unit is 931 mega electron volts. So recall the nuclear binding energy is the mass defect by the square of the speed of light, and the atomic mass of the nucleus of copper 63 is the atomic mass minus the mass of the electrons. So here we have 29 protons, so a neutral atom will also have 29 electrons. And we're given the mass of an individual electron, which is 0.0005486 atomic mass units. So therefore the mass of the nucleus is 62.9137 atomic mass units. And the mass of the individual nucleons making up the nucleus is the mass of the protons. So here we have 29 protons multiplied by the atomic mass of one proton plus the atomic mass of the neutrons. So here we have 63 minus 29 neutrons. And that's multiplied by the atomic mass of one neutron. So that gives 63.5075 atomic mass units. And from that, we can calculate the mass defect, which is the mass of the individual nucleons minus the mass of the nucleus of this copper nuclide. So that gives 0.5938 atomic mass units. And we're given the energy equivalent of one atomic mass unit being 931 mega electron volts. So therefore the binding energy is the mass defect multiplied by 931 mega electron volts per atomic mass unit. So that gives 552.828 mega electron volts. And here we have 63 nucleons. So if you divide this by 63, we get the binding energy per nucleon being 8.8 mega electron volts per nucleon. Uranium-235 is bombarded with neutrons and undergoes nuclear fission. So that means the nucleus gets split up into smaller nuclei. And we're asked to determine the number of free neutrons that are produced. Well, on the left hand side, we have a total mass number of 236. And on the right hand side, we have 140 plus 94, which is 234, plus our unknown number of neutrons. So if you solve this equation, you get the number of neutrons that are produced being equal to 2. So these neutrons will collide with other uranium nuclei to cause another fission reaction, and this continues, and you get a nuclear chain reaction that releases a lot of energy. Given the following data for the radioactive decay of a sample of radon-222 nuclei, determine the half-life, decay constant, and time at which 95% of the nuclei have decayed. Well, from the table, we can see that 50% of the nuclei have decayed after 3.82 days. So that's the half-life. And recall the expression for the number of nuclei at time t is equal to the initial number of nuclei by an exponential term to the power of minus the decay constant by time t. And given that we have the half-life, we have half of the nuclei remaining at t1 half. So we can cancel out the initial number of nuclei and take the natural log of both sides, which gives the natural log of 1/2, or 2 to the minus 1, is equal to minus lambda by the half-life, which is 3.8235 days. And this is the same thing as minus the natural log of 2, and cancelling out the negative signs, we can solve this equation, which gives the decay constant being equal to 0.1813, and given our time is in days, and this term's dimensionless, then the decay constant will be in units of per day. And when 95% of nuclei have decayed, we have 5% of the nuclei left over. So on the left hand side, we have 0.05 by n0 is equal to n0 by e to the minus lambda t. So we determine the decay constant multiplied by the unknown time t. So if we cancel out n0 and solve this equation, we get the time as around 16.5 days.